Alright, in this video I want to discuss Newton's second law. I also want to discuss the formulas for gravity, the gravitational force, and for frictional forces. And I also want to talk about force diagrams. I'll show you what those are. So let's get going. So we left off by explaining that we need a force for an acceleration. Okay, that was Newton's first law. Now, what was left unsaid was that if you do have a total force, if you add up all the vector sums of the forces, now how much acceleration do you actually get? Okay, and that's what Newton's second law is good for. So Newton's second law answers the question, okay, so now that you have an acceleration, how much do you have? Okay, Newton's second law says that, okay, well, the acceleration is going to equal the net force divided by the mass. Okay, so let's do an example. All right, so suppose we apply, let's push a couple of objects across a frozen lake, and I'm going to make it a frozen lake so that we don't have to worry about friction. Okay, so I'm going to push a small box. Let's say that this box is 3 kilograms. Okay, and I'm going to push it with 30 newtons. Okay, in order to find the acceleration, what I would do is I would say, okay, the net force is 30 newtons divided by the mass, which is 3. So I have a 10 meter per second squared acceleration. All right, now what if instead of that box I pushed a box, a much bigger one filled with rocks, and let's say that the mass of this guy was 30 kilograms. Let's see what the difference is now. Okay, now let's push it with the same force, by the way, 30 newtons. Okay, so now the acceleration for that case, again, 30 newtons divided by 30 kilograms. Now we only have a single meter per second squared. Okay, so as we increased the mass, Newton's second law gave us a smaller acceleration. All right, now that you may have predicted that from when we were talking about inertia, right? We said that more inertia, more mass means more resistance to acceleration. So the red box has more inertia, so it's going to fight us more. Okay, so the 30 newtons is not going to deliver the same amount of acceleration. Okay, so you'll use that in several homework assignments. It's a very nice, simple formula. Straightforward, so I hope that that's pretty clear now. Let me give you the formula now for gravity. Okay, so we've already talked about if something falls free fall, it has an acceleration of 9.8 meters per second squared. That's often called lowercase g, and it's about 9.8 meters per second squared. All right, now the gravitational force on a mass m, let me give you that now. The gravitational force on a mass m is mg. All right, so gravitational force is the product of mass and that free fall acceleration. Okay, this force is often called the weight of something. All right, we've often heard people say, you know, what's your weight? Okay, when they're asking you what your weight is, they're asking you what's the force, what's the pull of gravity. Okay, if something weighed, I don't know, let's say 60 kilograms. Okay, then to find the weight, to find the force, the gravitational force, we do mg. So we do 60 times 9.8. That's going to be about, roughly about 600. Okay, so roughly 600 newtons. Okay, You can do that. You can get a more accurate answer on your calculator, but roughly about 600 newtons. So it would be correct for you to give your weight in terms of newtons. In fact, you can look for how to convert pounds, which is another unit for weight and force, convert that to newtons. All right. It turns out that 1 pound is let me put it this way. 1 pound is 4.45 newtons. All right. So when you go to the store and you buy a pound of apples, you could just as likewise say say that you're buying about 4 or 5 newtons worth of apples. Okay, that would be about the same thing. 4.5 newtons, 4.45 newtons worth of apples. Okay, so there's the formula for that. You might want to find what your weight is in newtons. Okay, now let's do friction. Okay, so the formula for friction is going to involve 2 things. The amount of frictional force depends on 2 things. The type of surface, the type of surfaces. Okay, so clearly if you're trying to drag a couch across a piece of sandpaper, that's going to be easier than trying to drag it across a frozen lake. So the surfaces matter. Okay, and also depends on how much force is pressing the 2 surfaces together. All right, so let's discuss what I mean by that. So, yes, so if you're dragging a couch across the ground, okay, or something, a box across a lake or whatever, if the surface is rough, it'll be more difficult, so it depends on the surfaces. Now, what if somebody decides to sit on the couch while you're pushing it? Then it's going to be harder to drag the couch. Or if somebody puts a backpack on top of that box you're trying to slide across the frozen lake, then it's going to be more difficult to push, isn't it? Okay? The reason it's going to be more difficult is there's more friction. Why? Because now that you're pressing into the ground more. Okay, you're pressing into the surface. So that's what I mean by number 2 here. Okay. Now, usually when you're pressing into the surface, there will be an equal and opposite normal force pushing against you, so that you don't actually move into the surface. So let me combine both of those now. All right. So the type of surface, the strength, the amount of friction for different combinations of surfaces are given by a constant, and that constant is denoted by a Greek letter, mu. Okay, it's called the coefficient of friction. I would encourage you to do this right now. I would encourage you to search the internet for tables of coefficients of friction. If you do that, you will see, like the friction of glass on glass or metal on metal, different types of metal on metal, etc., etc. Okay, and you'll see that you'll have different numbers, and then as a surfaces get rougher, you'll see that the coefficients will get bigger. Okay, and then the force pressing 2 surfaces together, I said that there's usually an equal and opposite normal force to counteract that. So that's why we denote this by N. Okay, so putting it all together, the frictional force is equal to that constant times the normal. Okay, now actually that's the biggest that the frictional force can be, so I'm going to say less than or equal. Okay, why do I say less than or equal? Okay, so suppose that you were, suppose that I wasn't, well, here, let me make another picture. Pictures are always good to help explain things. So I have a box. Today's the day to push boxes across rug carpet. Okay? And so if let's say that I am not pushing the box. Okay? What are all the forces acting on the box? Okay, let's draw some arrows to denote the strength and direction. Excuse me. So we've got gravity down, which we know now is mg. We've got the normal force, which we know now is equal to mg, right? They're balancing each other out. Do we have any horizontal forces? The answer is no, because, well, we're not. Friction only shows up if we're trying to actually move it horizontally. Then it gets annoying and tries to get in our way. Okay, so right now there's no friction. Okay, now suppose that some little kid comes by, and suppose that some little kid pushes this with 5 newtons of force. Okay, if they push it with that, then the box, let's say that the box doesn't move. Okay, then the friction is going to be 5 newtons to balance it out. Okay, now let's say the older brother comes by and pushes it with 15 newtons of force. Okay, then the friction all of a sudden goes up to 15 to balance it out. Okay, and let's say another older brother comes by and pushes it with 115. Well, then the friction becomes 1. So you see how the friction could keep growing and growing and growing, and you see how friction's annoying, because whatever you decide to push with, friction says, okay, I'm going to match it, right? Now the normal is like that too. Notice that however hard you press into the surface, the normal is going to be just enough to balance that out. Okay, so the normal adjusts as well. Okay, however, that only works up to a point. Eventually, there's going to be some amount of pushing that's just going to get the box to start moving, right? Okay, right when you do that, right when you have the maximum push, let's say it occurs at 1,115 newtons. Okay, that maximum push where you're finally overcoming friction, the maximum friction, that's what the mu times n is. Okay. So, for example, suppose you looked up in your table of the coefficients of friction. Suppose that for this example that I gave here, suppose that the mu was 0.2. And suppose that this box had let's say it was 100 kilograms. Okay, so the gravity would be 100 times 9.8. So the gravity is about 1,000 newtons roughly. Okay, it's actually 980 if you want to be exact. Okay, so the normal force up is going to be about 1,000 or 980 newtons to balance it, right? And what about the friction? Well, the friction is going to be mu times the normal, so 0.2 times 1,000, which is 200. That's the maximum it could be. All right. So for the example that I have here, the 1,115 newtons would actually be more than the friction. So let's correct our situation. So here we would have a friction of roughly 200 newtons. Okay, and so what would the net horizontal force be? Okay, so let's use now Newton's second law again. We'll make this a Newton's second law example. Okay, so we've got the net force. We would have to do a vector sum, right? So we're pushing with 1,115, but then there's an opposing of 200. So the net force, let me do it at the bottom of the screen, would be 1,115 minus 200, which would give, let's see, 85, so 915 newtons, right? That's the net force. Now, the acceleration would be the net force, 915 divided by the mass, which is 100. So 9.15 meters per second squared. All right, there's a great example using friction for you. Okay, and I also drew a force diagram. You saw that I drew arrows for all the different forces acting on this body, on the box. Okay, let me make a couple other comments. Okay, mass. Let me go back to gravity. Mass is not the same as weight. Mass, first of all, they have different units. Mass is measured in kilograms. Weight is measured in newtons. Okay, on a different planet, the G won't be 9.8. It'll be more or less. Okay, but the mass will still be the same. Mass, loosely speaking, is how much stuff is there, right? How many atoms, okay? Whereas the weight has to do with how much it's being pulled, okay? Completely different things, okay? If you were up in space, you would be what they call weightless. If you're weightless, then there's no total force acting on you, right? Okay. However, there is no when you're weightless, you feel like there's no force, but you still have mass. Okay. So again, mass and weight, mass and gravity are not the same thing. Okay. Now let me a couple other examples for you to think about. Suppose that I had a car driving down the freeway and it was cruising. So you're cruising at 65 miles per hour. Okay, what is the total force acting on the car? So we said from Newton's second law, we said that the acceleration is the total force divided by the mass. Okay, now, or another way to write Newton's second law is to say that the total force is the mass times acceleration. So if I'm cruising down the freeway with no acceleration, then m times 0 acceleration gives 0 newtons, so I have no total force. Well, if I have no total force, how come, for crying out loud, I have to keep burning gasoline and running the engine? Okay, why is that? Okay, well, yes, you have, the answer is yes, you have no total force, but you do have friction, so you have to run the engine just to overcome the stupid friction, the air friction and the friction from the ground. Okay, so that's why that happens. All right, here's another example. Suppose that I had a elevator cart with a bunch of equipment and people. Okay, suitcases, luggage, and let's say the whole mess was 20,000 newtons. All right, and now I have a cable that is pulling everybody up at the speed of, let's say, 5 meters per second, all of that mass. Okay, what is the net force on the elevator compartment? The total force. Think about that for a minute. Okay. Ready for the answer? So the net force, even though that would be a very difficult thing to do, the net force, or the total force, is 0. Okay, you say, well, hold on, how could it take no total force to move that? All right, well, I didn't say it takes no force. I just said that it just turns out that the total net force, the net force, is 0. Okay, how could that possibly be? Okay, well, let's draw a force diagram. We've got gravity pulling down, and we've got, oh, I haven't mentioned this force. When you have ropes and cables, that's called the tension force. You can add that to your list of examples. Okay, so we've got tension T and mg for gravity, and they're both going to be balanced. Okay, the amount of the tension, the strength of the tension, is equal to mg. So that's the reason that the net force is 0, even though you've got these two huge forces. Okay, so think about that. All right. Now, let me close with that example.